you guys this. I have a couple of handouts. One we'll work on together, front and back, and then I have one for you to try on your own. This deals with 4-3 and 4-5. So this is stuff we got into, we did it for a couple of classes, I think, just about. Let's see. Fancy pen. Let's see if you work. There you go, Jeff. Too fancy for me. So what the newest thing we've learned recently is what a second derivative tells us. Can somebody tell me what all can we get from the first derivative by itself? I mean, I know first derivative means slope, but what can we get from it now? What can I use it to find about the graph of a function? Critical numbers, all right. So I can get from the first derivative critical numbers. How do I get critical numbers? They're where what happens?
The zeros
of
the
derivative or
it's undefined.
Or it's undefined. I love it. Kick ass. And if I do that, I make that sign diagram. And what does that sign diagram directly tell me? Indirectly tells me that. What's it directly tell me? When I put the pluses and minuses? That's where the function is. No, not concavity yet.
Negative and positive slope.
Yeah, so that's where the function's increasing, decreasing. And so it naturally leads itself to telling us where the maxes or the mins are. And of course, why are critical numbers? Why might I have more critical numbers than I do maxes and mins?
They should not be a max or a min. It could just be like a rest.
I love it. It could be like a little, I tricked you, right? I'm going to turn. No, I'm not. Kick ass. I love it. Very similar things happen with the second derivative, right? We still call them critical points. But now, what could they be? Not maxes and mins. They could be locations of inflection points, where it changes from like concave down to concave up. Or it's another like resting place. It's a little bit weirder to envision with second derivative, but it just is where, if it's where the concavity goes to 0, but it doesn't change sign. The simplest function where that happens is, let's see if I can find some paper. If I look at this function here, what's the first derivative? 4x cubed. And the second derivative? 12x squared. I like it. Cool. So look at this guy for concavity. What would I put on my little sign diagram to investigate the concavity of this? Where's the 0 for this guy? 0. You gotta look. When x is 0, it's 0, so I'm going to put a little z up there. Now, hopefully you can tell on either side of the 0, it's not going to change sign, right? I put a negative a billion in, it's positive. Put a positive a billion in, it's positive. So what's that mean then? What's true down here? What's true about the function? It has what feature? Yeah, concave up. It's happy. Yay. And what about up here? It's happy. Yay. So, but what about right here, the concavity is 0, which is kind of a measure indirectly, but later you learn what the real curvature is, but this is kind of a measure how flat it is. So x to the 4th gets pretty flat at 0, not like extremely flat, but a lot flatter than x squared does. All right, maybe. So there is a location where the concavity is 0, but it doesn't change sign. So is that a location of an inflection point? Is that a true inflection point? What's an inflection point mean? What happens around an inflection point? The what? The concavity changes. The sign changes for second derivative, which means the concavity changes. Is that an inflection point? No, concavity didn't change. Okay, I like it. So there's a lot of really good analogies between the work we do for f prime and what it means graphically, and the work we do for f double prime and what it means graphically. Okay. So, coming back down to this, y'all. Let's do this stuff together, and then you're obviously going to have your own stuff to work on in a minute. If I do f prime for this is nice and easy, so I'm just going to do it. Anybody not get this sheet? I just gave this sheet out. Anybody need a copy of that? Okay. All right. And then, of course, what can I do with that? I can take out 15. It's always nice when you have a verify thing. It kind of gives you a clue what the hell to do. But you guys can see that. And then, of course, how do I factor this guy? Probably like this, but it's because this guy, of course, is a difference of squares. 1 minus x, 1 plus x. Hopefully you guys notice if you write this the wrong way around, it's going to mess everything up. All your signs will be wrong. Everything's going to just suck after that. You're going to have it going up when it should be going down. All that kind of stuff. Okay. All right. All right. So that is definitely nothing new. Critical numbers are, of course, where this thing is 0 or where it's undefined. This is a beautiful polynomial, so no undefined places. What are the critical numbers?
0, 1, and -1.
Beautiful. I love it. Because that makes the derivative 0. We talked about multiplicity to try to make the next step quicker. So what's my sign diagram going to look like? What I'm going to have on this sucker? It's kind of a silly question, right? The things we just said, Jeff. Oh, yeah. So let's say -1, 0, 1. Now we're going to see today finally a place where this is undefined, and I put a little u up there. But these are all z's because it makes it 0. And what's the only one of these roots that it's going to stay the same sign on both sides? 0, because it comes from a even multiplicity. You don't have to use multiplicity at all if for some reason you hate it. I don't know why you would. It makes it so much quicker. So if I put negative 18 billion in, I get positive, positive, negative. Why did I pick negative 18 billion? Just to be dramatic. You just pick -2 if you want to. Right? And then, of course, it's going to change sign, stay the same sign, and then change sign. All right, cool. I like it. So a lot of the work we're doing is work you've done before. It's just kind of reorganized a little bit, which is really a lot of math. You learn a little new stuff, and then you do a lot of old stuff with that reorganized. So what does this tell me? It's what can I put underneath here? If I don't want to be really specific with a shape, I can just, what does this mean? The function is What happened? The function is got a negative slope, so it's decreasing. Here it's increasing, here it's increasing, here it's decreasing. Now, if you want to, you could be a little more specific for yourself. And this is really not that far away from this, but you could do like we did the first time. It's going down, it's flat, going up, flat, going up, flat, going down. I didn't really give myself enough room to do that correctly, but draw little arrows or draw like an actual little Loch Ness monster kind of shape. That's what most polynomials look like, is some kind of Loch Ness monster. I'm assuming, never seen it before. So where's this sucker increasing? It would be from, why would I be wrong if I said negative 1 to 1? Why am I wrong if I say it's increasing from negative 1 to 1?
Because it has a resting point.
Yeah, it's got a resting point. So where's it increasing? Negative 1 to 0, it rests for a second. And then it goes from 0 to 1, it's increasing again. And then it's decreasing everywhere else. Where's the map? There we go. So does it have a minimum? Does it have a minimum? Is there a point that it's going down to it and then it's coming up from it? Yeah, so it's got a minimum, it's going down, and then coming back up. So it's got to be a minimum there at negative 1, what? So now I got to plug it in this sucker. And I try to make a big deal out of that. You've really got to be careful about, do I use F prime for what I'm doing right now? Do I use F? Do I use F double prime? So yeah, you should get, I think it's negative 2, right? Negative 2. And there's a what here? Max at 1, and now this one's going to be 2. So you start to see a lot of, not every function is going to do this, but a lot of these polynomial functions and so forth, they're going to have some symmetries to them. We've seen this a couple times already, where you get the same output, just different signs. Okay, I like it. So then, what do you guys think I'm going to start to show this? I would not use this to try to do this. Because what would this involve? 3 applications of product rule. Oh my God. I don't want to deal with that shit. I'd much rather, here's F prime. This is another way to say F prime, but I'm going to use this thing. Yeah. You guys see what I'm saying? So everything I'm trying to tell you are mistakes, or not mistakes really, but just there's better ways to do some things I see students do. Use the better form to do the next derivative. So what's the second derivative going to be then? I know it's supposed to be this, but directly from here I get, that might be too easy a question, 30x minus 60x cubed. And then what comes out of there? Probably this. Okay. So I can take that 30x out. I'm left with 1 minus 2x squared. Now you guys take a minute and find the critical numbers. All right. So you get x is 0, or 1 minus 2x squared is 0, so you end up with, what do you get there? Yeah, good. Plus or minus 1 over square root of 2. Does that sound familiar at all? What's that related to? It's not really related to it through this problem at all, but what does that number look familiar at all to anybody? Yes, it should. What's it related to? Unit circle. Thank you. Sorry. I like it. Getting old. Hearing's going. And why is that? Oh, real quick. You guys don't want to hear this, but there's a trig identity. 1 minus 2 sine squared equals cosine, or 1 minus 2 sine squared equals cosine 2 theta. So this is kind of, this little function here is related to that trig identity. Anyway, has nothing to do with this function. It's just an interesting little side note. Okay. Or not interesting at all. Okay. All right. So now when I make my sign diagram, I've got 3 critical numbers to put on this bad boy. What's my multiplicities here? I didn't really factor this, but you should be able to tease out the multiplicities for each root. What are the multiplicities for each root? Yeah, they're all first, yeah. The 0 shows up once. There's 2 of these, but it's one of each of those. So they all show up once. So it's going to change signs everywhere. So all I got to do, unfortunately I can't use 0. Oh well. So let me put in there 30. Positive times negative is negative. Is that cool? It doesn't matter what number you pick. So there will be, what's it here? Positive, negative, positive. Just to double check, if I put in there negative 30, I get negative times negative is positive. Yeah, I like it. I like it. So if you don't trust that multiplicity thing, you can always just do each region. That's fine. So what can I put underneath this little region here? What's happening in here? It's happy. Concave up, down, up, down. So how many inflection points do I have? 3. Good. I got 3 inflection points. Kick ass. So my inflection points are negative 1 over add 2 comma something. Remembering that we are going to graph this by hand, throw this in the calculator and round it to a single decimal place, right? Another inflection point at 0, that one I'll do. Yay, Jeff. And then another one probably symmetric with that one. I have no idea what it's going to be. It's going to be gruesome. Let me see. You going to really try this in your head, Jeff? No, I'm not. Everybody help me out. Just throw that. Where am I putting that, by the way? I'll tell you where to put that, Jeff. No. Where am I putting this? To complete this point.
In the original.
In the original function. I love it. It's so damn easy to get. So you just plug shit into this guy, and then you go and plug this thing. Well, if you plug this in here, what am I going to get? If I plug this in here, I'm going to get 0. Yeah. So then that freaks people out. They end up with these flat functions like, what's going on? Well, you want a point, you've got to use the original function. You know that. But it's so many levels of this function, so many derivative levels, you really got to tell yourself, which one do I need to use right now? So let's see. If I put this in here, let me do this. 1 divided by, this is kind of cool, square root of 2. Store that in x. then I can just do 5 times x cubed minus 3 times x to the 5th power. Is this you guys, anybody doing that? I get 1.2 roughly. You can see that's kind of nifty. A little stow button. Do you see a little, if you have your calculator, there's a little stow button, store. So I can store this value in x. There's my x button. And then I can just type the freaking, I didn't even really need the times, to be honest, but, or you just plug the thing in there. Either way. So 1.2. So I'll bet you anything this is going to be what? Oops, what did this? I did this one. I bet you this one should be negative 1.2. And if I want to do that real quick, I can go back up here and say negative, redo this, and I get negative 1.2. Wow. Yes, ma'am.
What if we have a question where we have the second derivative, but we don't have the original equation? Do we have to guess what the original equation was by going up?
Yeah. I think I had that as a bonus question or something. I can't remember. Somewhere. Or we've looked at that kind of thing.
That's correct, but we didn't go to that.
No, because we're not. The reason we're not doing that yet is because we're still in derivatives, and that's anti-derivative. That's like going backwards, which is really the focus of chapter 5 and beyond. But we have done something like that. So, I mean, real quick, if I had this, now it gets worse the harder the function is. I mean, there are functions I could write down here that it's actually truly impossible to figure out what f was. There are functions you can't anti-differentiate. And so they're nifty. But, like polynomials are simple. Or even if I did this, now watch, even if I did this, you should be able to tease this out. What if I have this? This one's really simple too. You just got to think backwards. So what would I have taken the derivative of to get to cosine? Sine. See, and if your brain wanted to say negative sine, it's because when you learn the opposite of a process, you have the shifting gears problem, right? I can smell the smoke. So that's what's going to suck about the next part of the class, is it's all going to be different derivatives in reverse. And especially, I mean, this is a real easy one to get, oh shit, I could totally memorize cosine goes to negative sine, but this is going backwards. Yeah, so it would have come from sine. Now what's wrong with me just writing this? There's something wrong with me just writing this. And what's this, of course, represent? Some constant, because what's the derivative of a constant? So that's the weird, when you take derivatives, you might lose information because parts of it go to 0. So if you're thinking backwards, you have to put in there a general placeholder. Now, this is where things get really neat. Where's sine come from? Negative cosine. Where would c have come from? Where would a constant have come from? Cx plus d, kick ass. And to figure out what c and d are, I'd have to give you information like, oh yeah, f of 3 is 2 and whatever. You could plug that stuff in there, figure out what they are. That's going to be in our future. I like it. But I do like to bring it up every now and again because it really, if you can think about derivatives backwards and forwards, then you really know derivatives. Yes?
So, like, say you're doing a third derivative working down, would you
Yes.
put e or would you skip e? Because
So let's do one more step. Very often the next step after f is big ass F. That would be the next antiderivative. And then after that, we don't make a bigger F, we just sort of stuff. But where would this have come from? Negative sine x. And here's where things get interesting. It would have come from cx squared, but what's wrong with just doing that? Because what's the derivative of cx squared? 2. Oh shit, I don't have a 2 here, do I? So what's got to be here to kill that 2? Huh? No. Over 2. So the 2 comes down, now it dies. And of course, this will be dx, and then I have to have a freaking e now, right? Or maybe you don't want to use e, so you don't think it's Euler's constant.
That was my question.
Oh, I see. That's a really good point. Yeah. Sometimes you'll see, some books don't care, but some books will not use e. Sort of like the 13th floor of a hotel, but you just want to be really clear and eat it and suddenly magically show up. All right, I like it. Nice little side note. This will someday be all we're doing is derivatives in reverse. Okay. So now, let's make this more official here. Where's it concave up? What intervals? Well, it's going to be negative infinity to negative 1 over rad 2. And then 0 to 1 over rad 2. And where's it down? This is going to be the rest of it. Negative 1 over rad 2 to 0. A little u in there. Where'd I go? 1 over rad 2 to infinity. Woohoo! All right, that's easy. You just get that right off your picture, right? But I like to make you write intervals because some of us need practice with intervals as much as we can get. All right. Now, intercepts. What are the intercepts for this bad boy? What's the obvious x-intercept? One obvious one. How do I find the x-intercepts? I just do what with it? How do I find the x-intercepts? So I love it when I teach this for the first time. I try to tell people. So in my last class, I had an equation with about 17 letters, 17 variables in it. And say I wanted to find the w-intercept. What did I do? Made all the other letters 0. So if you want to find any intercept, you make the other letter 0. So here I'm going to make 0 in for y. Factor this bad boy. Gather x. So we get x is 0. Are you guys okay with this? Not a big deal. Finding x-intercept, set the thing equal to 0. Or I get x equal to square root of 5/3, plus or minus. So let's see, what is the square root of 5/3? 1.3? Neato. Become a 3. Okay. All right. No idea why I'm suddenly writing so sideways, but I will. Are those pretty numbers? No, but I don't care. I've rounded it enough that I can plot it pretty well, right? What about the y-intercept? Well, the y-intercept's got to be 0, 0, because that's the next intercept already. Why can't I have more than one y-intercept for this kind of problem? Because this is a function, and a function has to pass the vertical line test, so I can't have more than one y-intercept. Okay. So the very first thing I normally plot are my intercepts. They're my anchor points. Now, I want to figure out scale. So for my x-axis scale, what would I look at to figure out what a good scale is for my x-axis? From all the stuff we've discovered. So let me here's the most important stuff we did up here. Here's the most important stuff we did down here. And of course, all this stuff is important. What looks to be a good scale for my x-axis? Yeah, okay. So it goes down to -1 up to 1, right? And this goes to 1.3 for x. I want to see everything related to my important points and what x coordinates they use. So I really just have to see up to 1.3, a little beyond that. So if I'm smart, maybe I can make this like -1, -2, 1, 2. Are you guys semi with me? So Hopefully that's a little bit obvious. If you have a minimum at the point 11 comma negative 3, then I better be able to see up to freaking 11. I got to make my scale include 11. Okay. What about the y-axis? Looks to be about the same thing, except for my outputs up here have to go to negative 2 and 2, right? So maybe I could just make my y-axis a normal 1, 2, 3. What do you guys think? Does that sound all right? Okay. Let's just complete that. All right, cool. I like it. So I plot my intercepts. So before you plot any points, obviously the scale has got to be figured out before you start throwing points down. That should kind of make sense. So I got an intercept at 0, 0. I got one at 1.3 and negative 1.3. It's more like 0.40. Well, too bad. Make them big. Wee-haw. Those are my intercepts. Now what am I going to plot next? Yeah, good. So mins and maxes. So I got a min at negative 1, negative 2. So negative 1, negative 2. Let me put min underneath there. I got a max at 1, 2. Let me put max over there so my words are outside of my graph. It's a little tiny point, but still. And then, of course, I do the inflection points. I kind of like go back through all my work. There's an inflection point. What is negative 1 over rad 2? That's 0.7, I think, right? Roughly. You guys know what rad 2 is? Can you just tell me what square root of 2 equals? Approximately? Anybody? All right. 1.414, roughly. So rad 2 over 2 is going to be 1.4 divided by 2 is 0.7. So it's 0.707. So I get negative 0.7 here and positive 0.7 here. So at negative 0.7, negative 1.2, negative 0.7, so a little bit past negative 0.5, negative 1.2, there's an inflection point, and at positive 0.7, positive 1.2, there's an inflection point. That screen is really horrible. Sorry. Okay. So the beauty of this, some students try to use the intervals you've done to try to, oh my gosh, it's just so disgusting to try to keep everything in your head at once. So I'm not going to keep all this shit in my head. I'm going to plot it, indicate what it is, and that's going to help me as I go through these points. So what gets me started? I know that I am decreasing, and I know that I'm concave up to start with. Do you guys see that? I'm decreasing concave up. That's how I start. So decrease, that kind of makes sense. Decreasing concave up. So I'm coming in like that, coming in hot. And I go through this, and then I hit my minimum. What's going to happen at this point right there? Do you say I stop at that point? This is really good. You stop at the inflection points, because then you want to restart. Because it's really hard if you try to go through an inflection point and change the concavity. It gets a little bit wobbly and weird. Are you guys still with me? So it's concave up and decrease it. What's going to happen right here is it's going to become concave down. That's just a intercept, right? So I'm going to come concave down. It's going to get a little bit freaky through here. Concave down through there. What happens right here? Did I miss it? Oh, there's an inflection point there. All right, that was really not working well. Oh, I might have to restart. All right, let's see. So there's an inflection point right at 0, 0 that I forgot to label. Okay, so I'm going to go concave down through here. And what happens right at 0, 0? It's going to become... I might want to restart, but let's see. concave down. Oh, you're not going to work too well. Let's see if you're going to show up. Concave down, and then right at 0, 0 becomes concave up, and then what happens here? Concave down now. Goes through there, stays concave down. So what's going to suck a little bit is I have to grade. If you have something, I see students who will do something like this, a little wobble. That's the wrong concavity through there. So I'm not going to like every little wobble, because I have a lot of freaking wobbles here, but you got to really kind of overstate your concavity so I can see you understand how what you did computationally translates visually. That's the big thing between these. And that's why if you do this kind of work wrong, but your graph looks right, you're going to lose a lot of points, because you haven't demonstrated that you know how to translate what you found into a visual. So I'd much rather have this funky ass looking graph that's completely obviously wrong, but it totally matches your work. You're going to get a lot more points for that, believe it or not. Some students don't understand. My answer is wrong. Why? Because you showed me the most important step from algebraic to, or computational to visual. Okay, maybe. I like it. All right, I'm going to change things up a little bit because I've been talking for a long time. You guys go ahead and try the one on the back. A really beautiful, radical one. Yay, Jeff. Thanks for giving us this one, man.